Hey you guys, this is Mr. Millings, and in this video we are going to learn about rate laws, and we are going to learn how to find the rate law of different chemical reactions. So what is a rate law and how does it work? A rate law expresses the relationship between the rate of a reaction and the concentration of reactants. So what does that mean? Well, let's take a look. Let's suppose we have a chemical reaction in which A is reacting with B to produce C plus D over here. And we want to know the rate of this chemical reaction. Well, we'd have to write what is called a rate law for this chemical reaction. And the rate law is going to look something like this. The rate is equal to K times the concentration of our first reactant raised to some sort of power times the concentration of our second reactant raised to some sort of power. And so when we're talking about rate laws, the rate here is the rate of the reaction expressed in molar per second. In other words, moles per liter per second of the will be the rate of the chemical reaction. And this is going to be equal to K. K is our rate law constant. Rate law constant. And this is different for every single chemical reaction. Every single chemical reaction has its own K value, its own rate law constant. And so understand that concept. And so another thing you need to know about K is that the unit for K varies. It's going to change, and we'll learn about that in a different video. And the only variable that has an effect on K is temperature. Alright, so the only thing that's going to change K value for a specific chemical reaction is temperature. Okay, so rate equals the rate law constant times the concentration of our first reactant raised to some sort of power times the concentration of our second reactant raised to some sort of power. And so these here are concentrations expressed in moles per liter or molar. And these exponents right here, M and N, are called the order of our reactants. And so what is the order of a reactant? Well, the order of a reactant compares the concentration of reactant consumed over a given amount of time. So if we wanted to express or write a rate law for this chemical reaction right here, rate would equal K times the concentration of A raised to some sort of power, in this case the order of A, times the concentration of B raised to the order of B. So how can we figure out the order of our reactants? And how can we figure out the order of the entire reaction? And then how can we write a complete rate law for a chemical reaction? Well, let's take a look. Let's first figure out how to find the order of reactants and the order of a reaction. And so it says right here that the order of the reactant is a relationship between the concentration of the reactant that is consumed over a given amount of time. And so this can be calculated by taking a look at experimental data. So let's suppose we have this chemical reaction right here, A plus B producing AB, and we can see that this is an equilibrium. And we'll learn about equilibrium in a later unit, but just understand very quickly that what's also happening here is that AB is producing A plus B. It's an equilibrium. So we have A plus B producing AB in this chemical reaction right here. And let's suppose some students perform this experiment in the lab, and here are their results. So if we take a look at their results, in trial 1, the initial concentration of A that they used was 2.2324 molar, and they reacted this with 2.889 molar of B. And they found that the rate of this reaction was 11.672 molar per second. They do this a second time, except they change the concentration of A and they hold the concentration of B the same. And they find that the rate of the reaction is 2.918 molar per second. They do this experiment a third time, and if you take a look here, they've changed, or they've held the concentration of A the same as it was in trial 1, but they've changed the concentration of B, and they found that the rate of the reaction was this right here. And so what we have to do here is we have to find the order of our reactants, and then we want to know the order of this entire reaction. So in order to do this, here's what we have to do. Let's first start with reactant A. To get the order of reactant A, what we have to do is we have to take a look at reactant B. Let's take a look at reactant B, and what we're going to do is we're going to hold B constant. So if we take a look in trial 1 and 2, B is being held constant. It's not changing. And so let's take a look at the results for A. And so what we're going to do here to find our order is we're going to take the higher value of these two, and we end up with 2.324 divided by the lower value, 0.581. We're going to put this parentheses and we're going to raise this to some sort of power, in this case m. And we're going to set this equal to, now let's take a look at our rate over here, right? If we take a look at our rate, if we're holding B constant, then we'll see that the rate is changing depending on the concentration of A. And so what we're going to do here is we're going to take the higher of these two values and we're going to put it in our numerator, 11.672, and we're going to divide this by the smaller of our two values, 2.918. And if we put this in our calculator, we're going to get 4 to the m equaling 4. And so 4 to what power equals 4? Well, this is going to equal 1, right? M equals 1 here. Okay, so the order of A is going to be 1. So the order of A is going to be 1. This is a first order reactant right here. Okay? And so let's calculate the order of B now. To get the order of B, what we're going to do now is we're going to hold A constant. So we're going to hold A constant here and here. And then we're going to compare the concentration of B to the rate. And so we'll take the higher of our two values for B, which is 5.778, and we're going to divide this by 2.889, our lower of the two values. And we're going to raise this to the power of n. And this is going to equal, if we take a look, we're holding A constant in trial 1 and in trial 3. So if we compare the rates for trial 1 and trial 3, we see these two numbers right here. We'll take the larger of the two, 46.688 divided by 11.672. And when we put this in our calculator, this divided by this is 2 to the power of n, equaling this divided by this, which is 4. So 2 to what power equals 4? Well, n here is going to equal 2. So in respect to reactant A, we have a first order reactant, and in respect to reactant B, B is going to be second order. Okay, and so over time you'll start to figure out by looking at your table what will be a first order, second order, or third order reactant just by taking a look at the data. For example, if we hold A constant in trial 1 and in trial 3, we see that B is doubling. And if we take a look, the rate is quadrupling. So 2 to what power will give us 4? That is going to be 2. So you'll kind of figure that out along as you go. But if you don't know how to figure it out that way, you can always use this method right here. So the order of reactant A is a first order, and the order of reactant B is a second order, right? And so what if we're asked to figure out the order of our reaction? So in other words, what if we're asked to figure out the order of the reaction? To get the order of the reaction, it's simple. We simply take the order of A plus the order of B. 1 plus 2, which is equal to 3. So the order of our reaction, this is a third order chemical reaction. The order of our reactant A is 1, the order of our reactant B is 2, and we don't need to write 1 in the exponent here. We're just writing it to help show you what this means, but you would express this simply as A B squared. Alright, so understand how to figure out the order of our reactants and reactions So now let's apply this concept to several different examples where we write the rate law for different chemical reactions. In this first example, it says to determine the rate law for the following chemical reactions. So we have C reacting with D producing E, and here's our experimental data right here. It looks like we performed this experiment or this reaction on 3 different occasions here. And so if we take a look, we want to write the rate law for this reaction. And so to get the rate law, we know that the rate is going to equal the rate law constant times the concentration of our reactants, concentration C raised to the power of M times the concentration of D raised to the power of N. And so M and N are going to be the order of each one of these reactants. And so let's first figure out the order of reactant C. So if we take a look at C, reactant C here, what we will have to do is we'll have to hold reactant D constant, and we do so in trial 1 and 2. And so now what we're going to do is we're going to compare the concentrations of reactant C to the rates over here. And so here we go. Let's do this. If we take a look at these 2 concentrations, we're going to take the higher of these 2 concentrations, which is 1.36, divided by the lower of the 2 concentrations, and we're going to raise this to the power of M, and we're going to set this equal to the 2 rates when we hold D constant. And so if we take a look, we have these 2 rates right here. We're going to take the larger of those 2, which is 10.688, divided by 0.668, the lower of our 2 concentrations. And when we put this in our calculator, we'll get 4 to the power of M equaling 16. And so if we take a look, what's going to complete this expression? Well, 4 to the second power, or 4 squared, equals 16. So M here equals 2. So in respect to C, we have a second order reactant in C right here. Let's take a look at D now. If we want to figure out D, or what order D is, we're now going to have to hold C constant. So we're going to hold C constant in trial 2 and 3, and then we're going to take a look at the concentrations of D. We're going to pull the higher concentration and put it in the numerator, so 2.472 divided by 0.412, and now let's take a look at the rates when we hold reactant C constant in trial 2 and 3. If we take a look, they're both the same. So we'll take 0.668 over 0.668. We're going to raise this to the power of N. And so now if we take a look, this divided by this is 6 to the power of N equaling 1. And so if you remember, anything to the power of 0 equals 1, so N here is going to be 0. So in respect to reactant D, we have a 0 order reactant, and in respect to reactant C, it is going to be second order. So if we want to write our rate law for this chemical reaction right here, the rate is going to be equal to K times the concentration of C to the second power times the concentration of D to the 0 power. And because we know anything to the 0 power is 1, we can simply write this as K times the concentration of C to the second power times 1, in which case we don't even need to write this 1. So the rate law for this chemical reaction is going to be rate equaling K times the concentration of C squared, and this is going to be our final answer. This is our rate law for this chemical reaction right here. Let's take a look at another one. Oh, I'm sorry, last but not least, if we're asked to figure out the the order of this entire reaction, 2 plus 0 is 2. So in respect to the entire chemical reaction right here, this is a second order reaction. All right, so in respect to reactant C, it's second order. In respect to reactant D, it's zero order, and the entire chemical reaction is a second order chemical reaction because 2 plus 0 equals 2. Let's take a look at another example. In this second example, it says that we have C plus B2 producing CB2, and we've performed this chemical reaction on 3 separate trials. We've changed the concentration of C, we've changed the concentration of B2, and we're taking a look at the rate of the reaction when we alter these concentrations. And so we're asked to figure out the rate law for this chemical reaction right here. And so keep in mind that the rate law is going to be rate equaling the rate law constant, which is specific to this chemical reaction, times the concentration of C raised to the power of M, where M here is the order of reactant C, times the concentration of B2 to the power of N, where N here is the order of reactant B2 here. And so, in order to solve this problem, we have to figure out the order of reactant C, and we have to figure out the order of reactant B2. So let's figure out the order of reactant C first. So over here, we are going to figure out the order of reactant C. And the way that we figure out the order of reactant C is by holding the concentration of B constant in trial 1 and in trial 2, and then taking a look at reactant C and the rate of our chemical reaction. And so we're going to take the higher of our two values here for reactant C, which is 0.315, and we're going to divide this by the lower of our concentrations for reactant C, which is 0.105, and we're going to raise this to the M power, and we're going to set this equal to the higher rate over the lower rate. So 2.862 divided by 0.318. And when we put this in our calculator, we're going to end up with 3 to the M power. And when we put this in our calculator, we're going to end up with 9. So 3 to what power equals 9? Well, 3 squared equals 9. So in respect to reactant C, we have a second order reactant right here. Now let's take a look at reactant B2. So let's figure out what the order of reactant B2 is. And the way that we're going to do that is we're going to hold C constant, and then we're going to take a look at the rates. And so if we take a look here, we're trying to figure the order of B2 out. So we need to figure out the relationship between these concentrations here. We're going to take the higher of our two values here, which is 0.11. We're going to divide this by the lower of our two values, which is 0.055. We're going to raise this to the N power, and we're going to set this equal to the higher of our rates on top, which is 0.318. divided by the lower of our two rates, which is 0.159. And this divided by this is 2 to the N, equaling this divided by this, which is also going to be 2. So 2 to what power is 2? N here is going to equal 1. So in respect to reactant B2, we have a first order reactant. In respect to reactant C, it's going to be second order. And so how do we write the rate law now for this chemical reaction? Well, the rate is going to equal the rate law constant times the concentration of C raised to the M power, which is second order, so we'll put a 2 here, times the concentration of B2 raised to the N power, which is the order of reactant B2, which is a 1 right here. But we don't need to write 1s as superscripts or as exponents, so the rate here is going to equal K times the concentration of C to the second power times the concentration of B2. And so, what is the rate law for this chemical reaction? Well, it's right here. Finally, what if we're asked to figure out the order of this entire reaction? So we want to know the order of this reaction. The order of the reaction is equal to the sum of the order of our reactants. So we have 2 here for C, and we have 1 here for B2. So this is going to be a third order reaction. Alright, so this is going to be the rate law for this chemical reaction, and it is a third order chemical reaction. Let's take a look at another example. In this third example, it says to determine the rate law for the following chemical reactions. So we have 2NO reacting with Cl2 producing 2NoCl. And we've done this chemical reaction on 3 different trials. We've changed the concentration of NO here. We've changed the concentration of Cl2, and we've determined the rates of the chemical reaction. And so what we have to do is write the rate law for this chemical reaction. And so the rate law is going to be rate equaling K, the rate law constant, times the concentration of NO raised to the power of M, where M here is the order of this reactant, times the concentration of Cl2 raised to the power of N, where N is the order of this reactant right here. And so what we have to do now is we have to figure out the order of reactant NO and this reactant right here, Cl2. So let's figure out the order of NO. So we're going to figure out the order of NO first. And so to figure out the order of NO, we have to hold the concentration of Cl2 constant, and we do so in trial 1 and in trial 3. And so if we hold Cl2 concentration constant in trial 1 and trial 3, let's take a look at the concentration of NO, and let's also take a look at the rate. And so what we'll do here is we're going to take the higher concentration of NO, which is 2.64, and we're going to divide this by the lower concentration of NO, which is 1.320. We're going to raise this to the power of M, and we're going to compare it to the rates. Okay, so if we take a look, the higher of our 2 rates is 6.392, divided by the lower of our 2 rates, which is 1.598. And when we put this in our calculator, we end up with 2 to the M. And when we take this divided by this, we're going to get 4. So 2 to what power is 4? Well, M here will be 2. 2 squared is 4, so M equals 2. So in respect to reactant NO, it is going to be a second order reactant. Now let's take a look at Cl2. Let's figure out the order of Cl2. And in order to figure out the order of Cl2, we're going to have to hold NO concentration constant, and we do so in trial 2 and 3. And so we're going to take a look at the rates of trial 2 and 3 when we hold NO constant, and we're going to take a look at the concentration of Cl2 in trial 2 and 3. And if we take a look here, the higher of these two values here is going to be 0.726. The lower of our 2 values is 0.363. We're going to raise this to the power of N, and this is going to equal the higher of our 2 rates over the lower of our 2 rates. So 12.784 divided by 6.392. And so when we put this in our calculator, this becomes 2 to the power of N equaling this divided by this is also 2. So 2 to what power is 2? Well, N here is going to equal 1. So in respect to reactant NO, we have a second order reactant, and in respect to reactant Cl2, we have a first order reactant. So now we can write the rate law for this chemical reaction. The rate is going to equal K times the concentration of NO raised to the power of N times the concentration of Cl2 raised to the power of N. So rate here is going to equal K times the concentration of NO to the second power times the concentration of Cl2 to the first power. And so we don't need to write this 1 here. So rate is going to equal K times the concentration of NO to the second power times the concentration of Cl2. And this here is going to be our final answer. This is the rate law for this chemical reaction. So we have in respect to reactant NO, it's second order. In respect to Cl2, it's first order. So what is the order of this entire reaction right here? Well, to get the order of this entire reaction, we take the order of our reactant NO, which is 2, plus the order of Cl2, which was 1, and we will end up with 3. So this reaction here is a third order chemical reaction. Alright, so that's how you find the rate law for each chemical reaction. If you like what you see, go ahead and click that little bomb in the bottom right hand corner, and that will subscribe you to my channel. And feel free to leave any comments or questions in the comment section down below. And I really hope you guys found this helpful.